In this video, we're going to talk about something called the coefficient of determination, although this is more commonly known as R squared. Now, let's consider this small hypothetical data set where I have data on individuals' education and income. Now let's think for a second just about the variable on the y-axis, income. And we see that income across these individuals varies from just above $20,000 to about $70,000. So we could certainly calculate the mean income, we'll call it y bar, and plot that value on the scatter plot. And we see that 2 of the individuals are above average on income, and 3 are below average, although the person with 12 years of education, his income is just below the average for these 5 individuals. So we can think about measuring the vertical distance, the distance in the y direction, between each point on the graph and the average income, y bar. Now, roughly speaking, we can think of the length of these bars as telling us something about how spread out the data points are in the y direction. In fact, we're going to call this difference between y and y bar the total deviation. And now I'm highlighting this total deviation for one point in our data, but clearly we can calculate this for each point in our data set. And so what the total deviation tells us is how far away in the y direction is each point from the average y, or in this case the average income. So now, we have our incomes plotted against our years of education, and it looks like there's a linear trend to these data. As years of education increase, income tends to increase. So let's think about fitting a linear regression model to these data. So now here's the regression line that I've fit to these data. But now I want to focus our attention to just this one point. So now, we're going to look closely at this one point, but everything we're about to do here, you can imagine doing to the other 4 points on our graph. Now remember that y bar is the mean value of the y's, and we call the difference between the observed value of y and y bar the total deviation. And we can calculate it by simply taking y minus y bar. So in other words, it's the difference between y and y bar. Now, we can split up this difference into 2 pieces. The piece above the regression line and the piece below the regression line. The piece above the regression line is how much our line misses the point. That is y minus y hat, because y hat is the y value of the regression line. Now you'll remember that we've called y minus y hat the residual, or the error, because it measures how much our regression model has missed this data point. So another way to think of it is that this is the unexplained deviation in this data point. In other words, this is the deviation in the y direction that our model is not accounting for or not explaining. So then the piece below the regression line, which is y hat minus y bar, this is the explained deviation. It's the part of the total deviation between y and y bar which is explained or accounted for by the model. So pretty clearly, the total deviation between y and y bar is equal to the sum of the unexplained deviation and the explained deviation. That is, y minus y bar is equal to the sum of y minus y hat plus y hat minus y bar. And if you take a second to look at that equation, you can verify it for yourself. It's pretty clear that when we sum up the terms on the right-hand side, the y hat terms cancel out, and we're going to get y minus y bar, which is the expression on the left-hand side. Now again, everything we've done here to this one point, we could think about doing to each point in our data set. However, in the case of this one point, each of our three terms, the total deviation, the unexplained deviation, and the explained deviation, are going to be positive values. That won't always be the case. Depending on where the data point is relative to the regression line and the y-bar, some or all of these deviations could be negative. So what we do is we square these terms, which has the effect of making them all positive, and then sum these up over all the data points. In other words, the way that we split up the total deviation for this one data point into two pieces, we could do the same thing for each data point. And then if we square those individual pieces and sum them up across all our data points, we arrive at this equation. Now, it's beyond the scope of this class to show that this equation is true. However, we can still look at this equation and see what each piece represents. The left-hand side represents the total variation in the y values across all the data. The first term on the right-hand side represents the unexplained variation across all the data. It's a measure of how much our straight line model misses the points. And so the remaining term on the right-hand side represents the explained variation across all the data. That is, the part of the total variation that is explained by the regression model. So now, if we consider the fraction of the explained variation divided by the total variation, then this is the proportion of the total variation in our y variable that's explained by the regression model. And this is what's known as the coefficient of determination, or, as it's more commonly known, r squared. So the coefficient of determination, or r squared, it measures the proportion of the total variation in the response variable, that's the y, the proportion of the total variation in the response variable that's explained by the least squares regression line. Now there are a couple important facts. The value of r squared is always between 0 and 1. If r squared is exactly 0, the regression line has no explanatory value at all. If r squared equals 1, that means the regression line explains 100% of the variation in the y variable. But that will only happen if all of our data points lie precisely on the regression line. And so ultimately this means that r squared is a measure of fit. That is, it's a measure of how well our regression model fits the data. Now, let's go back and look at our cholesterol data set. Recall that we had data on total cholesterol versus age for a sample of women aged 25 to 65 years old. And we fit a regression model to this data. Our regression equation came out to be predicted total cholesterol, remember that's the response or the y variable, is equal to 151 plus 1.40 times age. Now, if we look more closely at the regression output, we see that the r squared statistic for this regression model is approximately 0.515, or we might round it off to 0.52. And so our interpretation of this r squared statistic is that 52% of the variation in total cholesterol, remember that's our y variable, 52% of the variation in total cholesterol is explained by the linear regression on age. Now, we can see how that value is computed by looking in the analysis of variance table at the sums of squares. The total sum of squares is the value of the total variation that we discussed earlier. The model sum of squares, sometimes this is called the regression sum of squares, is the value of the explained variation. And so, of course, the error sum of squares is the unexplained variation. And you can check for yourself that the model sum of squares plus the error sum of squares is equal to the total sum of squares. In other words, the explained variation plus the unexplained variation equals the total variation. Now, we can see how r squared is calculated by dividing the explained variation by the total variation. This gives us our value for the r squared statistic. And so, once more, we say that an r squared of 0.52 means that 52% of the variation in total cholesterol is explained by the linear regression on age. And of course that means that 48% of the variation in total cholesterol is unexplained by our model. So we can imagine there might be other factors such as weight or diet that might account for the other 48% of the variation in total cholesterol that our model is not accounting for. Now, there's one more point to make here. It turns out that our r squared is precisely equal to the square of r, the Pearson correlation coefficient. Now, our correlation coefficient for total cholesterol and age is 0.7178. Now, that value is rounded off a bit, but if we square that value, we get 0.515, the value of our model r squared statistic, rounded off to 3 decimal places. So this is a nice simple relationship between r, the correlation coefficient, and r squared. However, we need to note that this relationship only holds for the kind of simple linear regression model that we've been working with here. If we have some more sophisticated model, for example, we might have a model that has more than just one explanatory variable, then this relationship between r and r squared doesn't hold. It only holds in the case of what's called a simple linear regression model, the kind of linear model we've been looking at here with only one x variable.